So we're making great progress on planetary motion. So far, we've seen Kepler's second law, K2. So that's the one that says that equal areas are swept out by the radius vector in equal times for a planet rotating around the sun. And we've seen that Kepler's second law, equal areas in equal times, that's equivalent to the planet's motion being under a central force. So the only force acting on the planet in orbit is a central force directed towards the sun. So we went through the proof of that. That was something that Newton observed. But we haven't needed to know anything else about this force so far to prove Kepler's second law, just that it's directed towards the sun. So now we're going to need to use a little bit more about the nature of that central force. So let's just kind of remind ourselves of the general picture we had in mind. So we had our planet orbiting around the sun. So there was our planet. Maybe that was the Earth. There we go. So we're assuming that it's got just a central force. So the only force on the Earth moving around the sun is that force F directed towards the sun. And you remember the initial conditions we were assuming? We were assuming that initially at time t equals 0, the Earth was moving perpendicular to the x-axis at velocity v0, and that it was distance r0 away from the sun. Those were our initial conditions. And let me see, I'm just reviewing the things that we'd already seen last time. So we'd already shown, first of all, we'd considered, if you remember, we'd considered that position vector of the Earth, xy, with the sun at the origin, and we'd looked at the second derivative of that position vector. So that was the acceleration vector. And if you remember what we did last time is we computed that, we expressed it in terms of this unit vector, cos theta, sine theta. That was the unit vector, the vector of length 1, in the radial direction. And we'd found that x double dot was a scalar multiple of that vector, where the scalar was this function, r double dot minus r theta dot squared. When we were proving Kepler's second law, we'd done this more generally without this assumption of central force, and we'd had another term in there where that was the unit vector in the tangential direction, and it was by looking at the coefficient of that tangential direction that we were able to relate this Kepler's second law to the fact that there was no tangential acceleration, so that second component's just not there. Okay, so that was the important guy from that whole calculation, that formula for the radial acceleration. Okay, so we had that, and the other thing that we already observed was that this quantity r squared theta dot, that was a conserved quantity. We'd shown that was equal to r0 v0, so that was constant over all time. I might remind you about where that came from at the end, but that was the other ingredient that we'd needed when we were trying to talk about Kepler's second law, this equal areas being swept out by the radius vector. The fact that was a constant had exactly turned out to being that tangential acceleration was 0. So those were the equivalent properties there. Okay, so this property too, I'm going to use it a lot today. Basically, whenever you see theta dot, you can use this fact that r squared theta dot is a constant. You can use this to eliminate theta dot. Whenever it shows up, we're just going to replace it by r0 v0 over r squared and get rid of our theta dots. Okay, so that's where we're at right now. Now, I'm trying to prove Kepler's first law. So that's the law which says that planetary orbits are ellipses with one focus being the sun. So to do that, we're actually going to need to know exactly what this central force F is. Didn't need it for Kepler's second law, but to get ellipses coming out, we're going to need to use Newton's law of gravity. So I'm just going to state this today. So Newton's law of gravity tells us that central force F is given by the formula capital G, capital M, little m over r squared. So this is usually called the inverse square law because it depends on 1 over the radius squared. So in this formula, G is the universal gravitational constant. Which you can estimate in various ways, thinking about the moon rotating around the Earth or anything involving gravity like tides or something like that. This formula will let you measure something and then estimate what G has to be. And then there's two masses, the big M and the little m, which are at a distance r apart. Okay, so let's draw a little picture. That's one mass, that's the other mass, big M, little m. They're a distance r apart. Let's make that look a slightly straighter line for my force. There we go. So that's the force F. And because of Newton's conservation of momentum, every action has an equal and opposite reaction. So the big mass M is pulling the little m with force F, and vice versa, the little mass m is pulling the big M with force F in equal and opposite directions. Right? Each one is pulling equally on the other. We're going to be applying this to the sun and the Earth, and we're treating the sun as just though it's not moving. It's the origin, which is totally reasonable. I mean, the sun is incredibly massive, and the Earth is very puny and light. So the force on the Earth is going to accelerate the Earth much more than the little force the Earth is acting on this incredibly massive sun. Okay, great. So that's the force due to gravity. And what we're going to do is we're going to plug that expression for force in. We've got to do one more thing. We've got to use F equals ma. And so when we do this, we get that the force, well, actually, we should probably do minus the force, right? Because we measure R outwards, but the force is pulling inwards. So this formula for F, given by the inverse square law, I want minus F. That's my force in the formula F equals ma. So that's mass times this radial acceleration, right? So that the little mass of the Earth, and then the acceleration of the Earth towards the sun, this is this r double dot minus r theta dot squared. And then if we just plug in what the force is, that's this G big M little m over r squared. That's little m r double dot minus r theta dot squared. Okay, so it's just plugging in those two formulas into F equals ma. And I think I'm in pretty good shape. Let me see, what else should I do here? I think when you see, look right there, there's a theta there's a theta dot. And remember I said we were always going to use this conservation law, r squared theta dot is r0 v0. Whenever we saw a formula, we would use that to get rid of theta dot. So let's do that. So let me see. I think it's probably convenient to times through by this r squared. So I get some r's on the theta dot. Let me change signs as well. So that left-hand side just becomes G big M little m. On the right-hand side, oh, the little m's cancel, don't they? Look, there's an m here and an m here. So I should cancel those before I do anything. So then the left-hand side, I'm multiplying by r squared and changing the signs. So that's just big G big M is minus r squared r double dot. And then this gives me what? Plus r cubed theta dot squared, which is r to the 4 theta dot squared over r, and r to the 4 theta dot squared, that's this quantity all squared, so that's r0 squared v0 squared. Okay, so that's our equation that we've derived so far. That's what we're hoping to do, right? We're trying to use the laws of physics to give us a differential equation which we can then solve. And so here it is. Here's our differential equation. It's a second order equation. I must say it looks a little bit nasty. So I'm not entirely thrilled by that differential equation. And there's another problem here. We're trying to prove Kepler's first law, which is saying that the orbit should be an ellipse. We do know what ellipses look like in polar coordinates, but that equation is r in terms of theta. And there's no thetas in my differential equation at all. That's r in terms of time, my differential equation. So that's the other problem we've got to deal with. We want r in terms of theta, not in terms of t. So somehow we've got to do some rather clever manipulating of this equation to first of all eliminate all t's and get thetas everywhere. And honestly, this is sort of, you get these differential equations, the physical laws feed them to you, and then you're left with doing the math. Sometimes the math can actually be kind of difficult, and this is one where I think you have to be really you have to try all sorts of different tricks to work out what to do. When you're stuck like this, you've got a nasty looking differential equation and you don't know what to do, it's always helpful just to kind of take a step back and just to think, what are we expecting? We're expecting to be able to show that it's an ellipse. And we know the equation of the ellipse is r is, let me see, the general equation for conic section in polar coordinates. If you remember that was this general formula where for an ellipse, I guess we really want E. E was the eccentricity, remember. We want E to be between 0 and 1. So that's kind of what we're expecting for r. So I'm sort of thinking, what sort of differential equation could I have between r and theta? What could possibly produce such a formula? And I mean, it's rather nasty formula, you see, because it's what I don't like about it is that the cosine theta is on the denominator there. But maybe this suggests that if I change to variable u, which is 1 over r, this will work better. I don't know. I mean, there's a little bit of cheating going on that I'm giving you here in suggesting that this is meant to jump out at you. But you see, if I change from variable r to variable u, what's u? U is then the reciprocal of this thing. So it's 1 plus e cos theta divided by some constant. In other words, it's constant cos theta plus constant. So this variable u equals 1 over r, according to what we're expecting, what Kepler's first law is predicting for us. What we're expecting is that this variable u should satisfy this equation. And for this, I do know a differential equation which has this as its solution. This is not bad at all, because it's just a multiple of cosine plus a constant. So let's see what we remember. We know this differential equation, d2u by d theta squared plus u equals 0. Now, we saw that before when I was doing springy. That's the basic differential equation for oscillatory motion. Okay, I'm using u and theta, so it might not look just like that one, but it's the same differential equation after renaming those variables. This has general solution u equals a cos theta plus b sine theta. That's something I did a couple of lectures ago, was prove that general solution of that differential equation. We don't have that. We have d2u by d theta squared plus u. We want to add on a constant here, right? So I remember this was what I called a homogeneous differential equation because it had 0 on the right-hand side. But if I tweak it a little bit and I put a constant c on the right-hand side, this has general solution exactly what we're after. U equals a cos theta plus b sine theta plus c. And so the way this comes when you see these sorts of, this is a homogeneous second order differential equation. This one's inhomogeneous because it's got not 0 but c on the right hand side. This part of this general solution, this is the general solution of the associated homogeneous equation. When you replace that c by a 0, and then this c is a particular solution, just any one solution that works. And if you think about u equals c, when you plug in u equals c here, that's 0. Yeah, u equals c, yeah, that is a solution. Okay, so when you get an inhomogeneous equation, you think about how do you solve the associated homogeneous equation, that's this guy, and then you just have to find some random particular solution that's easy, and you add them together. That gives you your general solution. So that's of the form we're wanting, right? We're expecting our differential equation here, not for the variable r, but for the variable u, is going to have a solution of this form, a cos theta plus c. So it's going to fit into that framework. So this is what we're hoping. That if we set u equals 1 over r, our differential equation, which is this kind of nasty one that we've got, which is, what was it, minus r squared r double dot plus r0 squared v0 squared over r equals gm, will transform into u d, well, not, we want to get rid of the t and get thetas, so it'll be the second derivative of u with respect to theta plus u equals c. So that's kind of our plan. I'm just sort of trying to motivate why I'm going to make this crazy substitution u equals 1 over r, and I'm kind of hoping that when I do it, I'm going to be able to manipulate it to get this nice form, because this has the right sort of solution that I'm expecting, because I have Kepler's conjecture in front of me. So that's the plan. Okay, so we're going to take our differential equation, minus r squared r double dot plus r0 squared v0 squared over r equals gm, and I'm going to let u be 1 over r. So if u equals 1 over r, let's see, what's du by dt? So I'm just going to differentiate 1 over r with respect to t using the chain rule. So it's minus 1 over r squared, that's the derivative with respect to r, times dr by dt. But du by dt is the same as du by d theta by dt. Just remember, I'm trying to get rid of time, and I want derivatives with respect to theta in the end. But du by dt is du by d theta times theta dot. Let me see, if I multiply through by r squared there, what have I got? I got du by d theta, then I've got r squared theta dot is minus r dot. So I'm just cross multiplying by that r squared. And that's my conserved quantity. R squared theta dot, that's r0 v0. You see, and so I'm moving forward. I've got rid of quite a lot of t's. Let's differentiate with respect to time again. So differentiating the left-hand side with respect to time, it's the same as differentiating with respect to theta. So I'm going to get d2u by d theta squared. Then I need to times by a d theta by dt. So that's the left-hand side d dt, and the right-hand side gives me what, minus r double dot. So here's another theta dot. If I times through by r squared, I get an r squared theta dot, which is my conserved quantity, which I can replace by r0 v0. I've already got another r0, so I'm going to get r0 squared v0 squared is minus, remember I was timesing by r squared. So under this substitution, this is what it lets me do. It lets me take that quantity right there and replace it by d2u by d theta squared times this constant. So let's see what happens now. We're kind of getting very close. Our equation becomes, so minus r squared r double dot, that becomes d2u by d theta squared, and then I've got r0 squared v0 squared, right? That's so I've got rid of all the time derivatives now. It's all purely theta derivatives. And then what else did I have? I had r0 squared v0 squared over r equals gm. If I divide through by r0 squared v0 squared, that's d2u by d theta squared plus 1 over r is gm over r0 squared v0 squared. Oh, hang on. I don't want r's. I was trying to substitute 1 over r for u, so I should do that. I shouldn't write 1 over r there. I should just write u. And lo and behold, that's the form we hoped for. So it really has kind of miraculously worked out. But you know, there's sort of there's clues and things going on in the background, so that it's not completely crazy what's going on here. And from that differential equation, we know what the general solution looks like. U is a cos theta plus b sine theta plus c, and the c is this gm over r0 squared v0 squared. Okay, so that's our u. What else? So now I'm going to need to know what a and b are. So let me see. If that's u, du by d theta is going to be what? Minus a sine theta plus b cos theta. I just differentiated. When theta is 0, what's u? U is 1 over r. What was r when theta was 0? It was r0. When theta 0, u is 1 over r, and du by d theta, what's du by d theta when theta's 0? What have we got that will tell us that? Here's du by d theta. At times 0, r dot is 0, because remember our initial condition was that it was moving purely in the tangential direction. So at time 0, the radius length isn't changing. So at time 0, r dot 0, and so that gives us that du by d theta is 0 at time 0. So now I can plug in this particular value of theta, and when I plug in theta equals 0 here, sine of 0 is 0, cos of 0 is 1, so that gives me that b equals 0. And when I plug theta equals 0 in here, now that I know that b is 0, that gives me that a plus gm over r0 squared v0 squared is what u is at theta equals 0, which is 1 over r0. So that gives me a. It's not very nice. It's and did I get it all right? Let's see. It's yeah, I'm going to write it as, so this is my a. It's gm over r0 squared v0 squared. I'm just rearranging this equation. So I'm pulling this constant over to the right-hand side, but I decided to factor it out, so it's going to be a minus 1. So that's that constant over the other side. And I had 1 over r0, so I guess I'm going to want r0 v0 squared over gm. So I think that's just simply solving for A in that equation. So that gives us our A, and B is 0. And so finally, we've got what U is in the original equation. Now we found A and B. U is 1 over R. It's A cos theta right, that's A cos theta plus GM over R0 squared V0 squared. Okay, so why don't I just put a plus 1 there? Okay, it's still not looking very nice, is it? So let's see if we can just get that to work out one more little time. So I mean, we've got the solution. We've just got to do a bit of algebra now. That's what I had. So what does that say? If I take reciprocals, I've got what? R0 squared V0 squared over GM, doing reciprocals. So that guy there, it's 1 plus, ooh, I don't like that number. I'm going to let E equal R0 V0 squared minus 1 over GM. Can you see what I've got there? Hopefully that minus 1 is meant to be outside that fraction. And then what I've got here, it's 1 plus E cos theta. I'm guided because I'm heading towards the polar equation for the ellipse. Okay, so that's kind of looking quite good. I'm going to keep manipulating this thing. So what's this? So E plus 1 is R0 V0 squared over GM. If I times by R0, that would give me another one of those guys, right? And that's what I've got. So actually what I've got is that R is R0 1 plus E over 1 plus E cos theta, where E is this nasty R0 V0 squared over GM minus 1. If I do one more little trick, if I set V crit, I'm going to introduce this new thing which I'll call the critical velocity. If I let that be the square root of GM over R0, I know that looks a bit random. So what's V0 over V crit? That's, let me see, that's R0 V0 over GM square rooted. So if I square it all, that's, and I subtract 1, that's just E. I'm going to check that I did that right because it's looking a little bit doubtful to me. E is R0 V0 squared minus 1, right? So there's the V0 squared, and 1 over V crit squared gives me the R0 over GM. Yep, that's everything I've got there, and there's the minus 1. Let's write that down one last time. So this is our final solution. We've shown that if we let V crit be square root GM over R0 and E be V0 over V crit squared minus 1, then the solution of our differential equation for this planet's orbit is R0 1 plus E over 1 plus E cos theta. So, okay, that was, the algebra was a little bit nasty there, but we've derived that equation, and the important point is that this is the general equation for a conic section of eccentricity E. Okay, but I know this formula for E is rather nasty, and it involves this strange root GM over R0, but that's, I think, what we want. So now hang on, we were trying to prove Kepler's first law. So we were trying to show we had an ellipse ellipse, so we want this eccentricity to be less than 1. So we've got to think a little bit about eccentricity. Okay, so here's our solution, but so let's see if we copy that and just think a little bit. What do we know about this number e, this eccentricity? Why is it less than 1? Well, actually, there's a few cases. If it happens that v0 is greater than root 2 times this critical velocity, well, if that happens, then v0 over v crit is bigger than root 2. So when you square it, it's bigger than 1. So when you square it, if that's bigger than root 2, when you square it, it's bigger than 2. So this thing overall is bigger than 1, right? So that's the same as e being bigger than 1. That's one perfectly good possibility. Nothing's told us that v0 is not very fast. And if that was going on, it's totally plausible. What you'd get is you get a hyperbola as the orbit. If that initial velocity is really a little bit too fast, here's the sun. The planet is going to escape the sun's gravity, and it goes to infinity. I guess that's what we expect, right? If to have an orbit, your planet better not be moving too fast. If it goes too fast, it's going to just get away from the sun. It's never going to orbit around. And perhaps you know that if you fire some projectile in towards a planet. You've probably seen those science fiction movies when you kind of bounce their spaceship around an asteroid or something. That orbit that it makes when it bounces around is a hyperbolic orbit. It's not an orbit, it's a hyperbolic curve that it bounces around the planet and then shoots away in the other direction. Okay, so I guess it could be that v0 is root 2 v crit. That's exactly the case. E equals 1. Of course, that wouldn't happen in reality. Physical things are never actually exactly equal. But in that case, you'd be getting, it's a similar sort of story. You'd be getting, it would be a slightly different curve. It would be a parabola. But it still escapes to infinity. Then it could be that, let me see, the next thing that happens is that maybe v0 is between the critical velocity and root 2 times the critical velocity. So that's exactly when this eccentricity E is between 0 and 1. So this is more like what we were expecting. And indeed, this is exactly the case when you do get an ellipse. That's exactly what we thought we'd get. It could also happen that v0 is exactly equal to v crit. That's when the eccentricity is 0. We didn't really mind that, but again, that's a sort of not physically plausible situation. But you know, that's mathematically plausible, so we'd better include it. So that's, let me see if I can get that to draw in the right place. That's when you get a circular orbit. And then I guess it could be that v0 is really slow. And when v0 is less than the critical velocity, if you think about that, that's actually when the eccentricity is actually negative. Right, if v0 is less than v crit, then v0 over v crit is less than 1. So its square is less than 1. And when you subtract 1, you get that E is between -1 and 0. So actually, this one is another ellipse. I wasn't totally expecting it the way I've been drawing these pictures all the time. It's another perfectly good ellipse. It's just that the sun is not the right-hand focus of the ellipse. The sun is the left-hand focus. So this is another ellipse. This is the case when it's just the other focus. So, of course, we should have seen that that was a possibility all along, but in our standard equation for conic section, we always write 1 plus e cos theta. And we're assuming e is positive. Now I've got e being negative. The way you should think about that actually is you should think about taking this ellipse, which is kind of not the standard one because it's the wrong focus, and rotate it through angle pi. In other words, replace theta by minus theta. Because cosine is odd, if you replace your theta by minus theta, cos of minus theta, that spits out a minus sign there. And you get 1 minus e cos theta. So that changes this eccentricity to being a negative number. That's the way to think about that one. Okay, so there we go. We've now proved Kepler's first law from Newton's law of gravity. So from the inverse square law, we've shown that exactly implies that planetary orbits, at least the ones that are orbits, not escaping to infinity, are indeed ellipses. A circle is a special case of an ellipse, after all. You could turn this around. I'm not going to do it. But you could actually have started with the assumption that Kepler's first law was true. So assuming that the orbit was an ellipse, and essentially reversed all our arguments and proved that this force on the planet, which is a central force, has to satisfy the inverse square law. In fact, Kepler's first law, orbits or ellipses, is equivalent to Newton's inverse square law for gravity. So that's quite a nice thing. But instead, let's just finish by deriving Kepler's third law today. So finally, I want to try to derive Kepler's third law. So let's remember, this is the one that gives you information about the period T, capital T, for one full orbit. So I'm going to assume for this that E is between 0 and 1, so I can assume that, given that it's an orbit, by choosing the right initial conditions. Okay, so I'm in that case that I was expecting all along. Okay, so from the proof of Kepler 2, which we didn't do today, we did last time, we know the area swept out in time t is a half r0 v0 t. Okay, so that's something you've totally forgotten that. I'll just kind of really quickly remind you where that came from. We had this area function a, and by the formula for area of a sector, we knew that the area was a half r squared d theta. But we did a substitution because we wanted time. So if you replace theta variable by time variable t, then you get r squared theta dot dt there. And that's the guy that was our favorite constant, r0 v0, all along. And so you could calculate that integral. It's just integrating a constant, and we got this a half r0 v0 t. That was where that formula came from. Okay. The period t is the time when that area is the area of the ellipse. So we're looking for the value of capital T, the time where the area swept out in that time is exactly equal to the area of the ellipse. Okay, great. So now we need to know a little bit about areas of ellipses. So this is something that's really easy in Cartesian coordinates. If you're in Cartesian coordinates, we know the area of the ellipse. Well, if A equals B equals R, the ellipse is just a circle, and you all know the area of the circle is pi r squared. But the ellipse is just the circle stretched in the x direction to stretch r to A, and in the y direction is a stretch r to b. So just by kind of thinking about stretching a circle into an ellipse, I think you don't even need to calculate. You know that the area of that ellipse is pi ab. You could easily calculate that by doing exactly the same thing as we did when we proved the formula for area of a circle, starting with the Cartesian equation of the ellipse, x squared over a squared plus y squared over b squared equals 1. So we do know the area of the ellipse, it's just that we know it in terms of a and b. And that's a bit of a pain because we've got the sun here. Right? So when I was in Cartesian coordinates, that was the coordinate I would have called c. And if in Cartesian coordinates that was 0, the focus would have been at x equals c. And maybe you remember these formulas. C was AE, and E was the square root of 1 minus b squared over a squared. So that's all good. So unfortunately, we've got to kind of do a little bit of manipulating because we know the area in Cartesian, but we need the area in polar. So that's all that's going on here. So let me see. If that's the eccentricity in terms of A and B, B is going to be, B is going to be, if I just rearrange that equation to make B the subject, I think I get that B is A root 1 minus e squared. I think you can check that. That's not too bad. And this distance right here, that's what we were calling R0 in our problem, right? That was how far the initial planet position was from the focus. And if C is EA, C is, let me see, C is, so C is EA, R0 is going to be A minus C, which is A minus EA. So R0 is A1 minus E. I'm going to need both of those formulas as we go. So these are just kind of dumb little manipulating algebra because we're in polar coordinates and we know stuff in Cartesian coordinates. Okay, great. So what's the area? Area is pi AB, but B is A root 1 minus e squared. Okay, so that's what this will give us the period for one orbit, capital T. Okay, so I'm now gonna see if I can rewrite this a little bit. So what do I need here? Let me see. I need. So let's think if we can. Do we remember what V0 was? Let's go back and have a look. So from this formula here, 1 plus E is V0 squared over V crit squared. So V0 is V crit times square root 1 plus E. And V crit was that crazy thing there, right? Root GM over R squared. So that's R0. Okay, so root GM over root R0, root 1 plus E. Okay, so I'm going to plug that in right there for that V0 and see what happens. So I've got R0, V0 is root GM, root 1 plus E, and then I've got a 2, and I've got a root R0, T is pi A squared. I think this is going to just work out. Sorry, the algebra is just, this is always a slightly nasty place in the algebra, but it's not really too bad. I haven't yet copied this term here down, but I'm just copying that formula. 1 minus E squared is 1 plus E, 1 minus E by difference of 2 squares. So that's the formula I've got here. There's a 1 plus E there and a 1 plus E there. They cancel. that square root r0 cancels quite a lot of that r0. So that's all looking good. And I don't think I'm quite there yet. Oh, hang on. R0, if I plug in this formula right here for the R0 there, since R0 is A 1 minus E, when I square root R0, I'm going to get square root A square root 1 minus E root GM over 2t is pi a squared root 1 minus E. I'm sorry, I'm making this look very confusing. Then those cancel, and one more line, I get a formula for t. It's 2 pi. Oh, well, I've got a squared here and a to the half here. So if I divide a little bit, I get a to the 3 over 2 over root GM. There is this magic formula. So that was some effort to get that formula. Now, so that means that now Kepler's third law said that what you need to do is you need to look at the ratio a cubed over t squared, right? So a was this major radius of the ellipse, t was the period of the orbit. So what's a cubed over t squared? If I square the equation I've derived, and so I'm going to cross multiply a little bit, I'm going to have a gm over 4 pi squared. I've got the a cubed and the t on the left, I've squared it and then divided through by it. This is a constant, independent of R0 and V0, independent of the planet. This shows a cubed over t squared is constant for all planets. The constant's kind of unexpected, right? It's capital G, which is this universal gravitational constant, which you can estimate in a bunch of ways. Capital M is the mass of the sun over 4 pi squared. So if you calculate for your favorite planet, you work out, well, I guess that would be the Earth, right? If you work out what A and T are for the Earth, so you can calculate a cubed over t squared, you can work out the mass of the sun. So this formula is way better than Kepler. Kepler merely said that was a constant. He had no idea what the constant was. Newton's proof of Kepler's third law actually tells you exactly what that constant is. It's kind of a crazy number, but suddenly the mathematics is revealing things that the experimental evidence just would never have imagined. Okay, so we've done our job more or less. I'll talk just a little bit more about this next time, but we've now proved the Kepler laws, and so all of our efforts building this theory have paid off at this point.